Okay, so hello everyone. Today I would like to show you a rather simple but useful nonetheless project where we'll be implementing a convolutional neural network, or CNET for short, with the aim of performing a binary image classification. The dataset we'll be using is the cats and dogs dataset from Kaggle. And so let's get into the code. Now I have already imported some of the basic libraries we'll be using. We'll be using the TensorFlow and also the Keras API in order to import most of our models and parameters. Let's start by first of all creating the model. The model we'll be using is it's called a sequential. We can obtain it from the Keras API, and this is essentially a model, more like a linear stack of layers, where we can add layers one by one as we go. So now we have to create our first CNN layer. Okay, so let's take a look at our parameters. We'll be using a total of 64 filters. The kernel size is going to be 3 by 3, and as a padding method we will go with the same, which means that the output size equals its own input size. And well, the activation function is going to be a ReLU, a bit of a standard one. And regarding the input shape, since we are dealing with RGB images, which have a shape of 32 by 32 with 3 different layers, we will have to input 32, 32 and 3. So let's run the code. Good, everything seems to be working well. Next we want to add a what we call a maxpool layer. We are going to add a maxpool layer in order to reduce the special dimensions of the output, which is also a process called downsampling. Okay, there we go. The pool size will be 2 by 3, and for our padding method we have written down valid, which means that no padding will be applied. Good. And now we can proceed by adding our second CNN layer. As you can see, there is a much of a difference between the previous layers we have added. We won't have to specify the input shape in our second layer and the next ones as well. As for the maxpool layer, which again we need for further downsampling, is the same as the previous one. So let's run it, and good. Now we need to add a flattening layer. What the flattening layer does is we are converting our 2D matrix into a one and this way it will be we can use it to fully connect all of our layers. As you can see, the syntax is quite simple. All we have to do is just to import the flattened layer from Keras. And good, no errors so far. Now we can go with the not the output layer yet. We still need to introduce the dropout layer. The reason why we are adding dropout layer is because we want to prevent overfitting, and the way we'll be doing it is by making sure that 40% of the neurons will be randomly ignored during the training. In this case as well, the syntax is quite simple. We'll be importing the dropout layer from the Keras API, and since we wanted to ignore 40% of the neurons, we will be specifying a parameter of 0.4. And now we can finally close our model by adding our final output layer. Although first we actually needed to add a connected layer as well. Okay, great. We have our output layer. A dense output layer is a layer with a single unit and an activation function, which in our case is the sigmoid function. And what it does is that the output will be a value between 0 and 1, which makes it quite useful and suitable for binary classification purposes. Okay, so now that we have all of our layers, we can finally compile the model itself. Okay, so our optimizer will be ADAM, again another standard method, obviously. What the ADAM optimizer does is it adjusts learning rate dynamically. Then we'll be using binary cross entropy as our loss function. Which again it is the one of the most appropriate ones for binary classification tasks. And last but not least, we'll be using the accuracy metric, which is tracked to monitor our model performance. So let's compile the model, and okay, good, we can ignore this error. And now we can actually fit our CNN model, or we can fit our data, our images to our CNN model. Okay, again, we will be using Keras for our fitting process. We probably, since we are dealing with images once again, we need to import the image data generator. I will show you just in a second why we need it. And also we needed to create two variables, one containing the directory for the training data, and the second one for to contain the directory for the test data. Again, this depends on where you'll be saving the files. So now we can finally rescale our images. Okay, good. So the reason why we imported the image data generator is in order to rescale the pixel, and that's why we have a value of 1/255, which means that the values of our images will go from being in a range between 0 and 255 to simply 0 and 1. Next, we need to, once we have rescaled our images, we can declare our training sets and test sets. Again, the target size will always be 32 by 32. Our two classes are dogs and cats. Class mode, again, binary, since we're doing a binary classification. And as for the batch size, we will set it to 20 for both sets. Now we can take a quick look at some of the values of our training and test sets. Okay, so taking a quick look at the length of our training sets, all of the values seem to be reasonable, and our batch size, as we had specified it earlier, is going to be 20, so we can actually proceed with training the model. Okay, so we will be training the model by using the fit generator method. The training will run for 20 epochs with 401 steps per epoch. This is based on the data size and the batch size we had seen earlier, and therefore the validation will be done using, of course, the test set with 102 validation steps. Okay, and now we can let the training run and wait for it to be done. Okay, that was kind of fast. It only took about 16 minutes and 16 seconds. Again, my computer is not particularly fast, so it might be take less time in your case. Anyway, we had, as you can see, a total of 20 out of 20 epochs we had stated previously, and the results are they're kind of satisfactory. They're not bad. But anyway, we can actually visualize how well our model has fared by actually plotting a learning curve, so we can get a visualization of our training and validation accuracy and loss results. So let's start, and we'll be using Matplotlib, which had already imported, yes, here at the beginning. Good. Okay, this is going to be our learning curve function. We'll be visualizing the accuracy of the training sets between the validation set and the loss always between the training and the validation sets. Okay, so what can we see here? Let's start with the model accuracy first. What we can see is about after the fourth or fifth epoch, the validation accuracy is not increasing at all, and this means that we are overfitting. Whereas in the second graph, we can see that yeah, always around the fourth, fifth epoch, the training loss is decreasing, although the validation loss is not. And so these are the results we get. Again, if we tinkered a little bit with the hyperparameters and perhaps tried some other models, we could get better results, but I just wanted to show an overview of how a convolutional neural network for image binary classification purposes works. And I hope it was useful, and I'll see you next time.